Welcome to Brain Vision.
Okay, so we have a long wire up top here, which I've labeled as wire 1, and that has 3.5 amps of current going through it. And then down here we have a loop, or a rectangle rather, of wire that also has 3.5 amps of current going through it. And so this rectangle is 3 centimeters below the first wire, and then we have its dimensions down here as well. And so we want to find then what the net force on this rectangle of wire is caused by this long wire up top. So first off, we'd want to break this into 4 different sections for this rectangle. So we'd want to think of this current here makes a magnetic field, and then that will interact with the current flowing through this top part, and then the side, and the bottom, and then the other side. So the hard parts are going to be these 2 edges here, so right here and here. And that's because they're not at a constant distance away from this top wire. And so really then we'd have to integrate it to find what the total force is. But fortunately, there's some symmetry here. So over here we have the current going down, and over here we have the current going up. So we know they're going to produce opposite forces. And because they have the same current going through them, they'll be equal magnitude. So equal magnitude, opposite directions. And so these 2 sides are going to cancel out with the force they make. So we don't have to worry about those. So then we're just going to think about the force from this top segment of wire, which I've called point A or part A, and then this bottom segment, part B. So the net force then that's acting on the rectangle is going to be the force that wire A contributes minus the force that wire B contributes. And I'm saying minus because the current in wire A is going in the same direction as in wire 1. And so I know those are going to be attractive then. A is going to be attracted upward to point 1. And then B, the current's going the opposite direction, so it's going to be pushing it away. So I'm going to kind of treat this where the magnitude of force B is a positive number, and then I'm saying it's going in the negative direction. So I'm putting a minus sign there. So then each force we know is going to be the magnetic field acting at that point times the current going through there. So this is the magnetic field at point A, or along line A, times the current there, and then times the length of the segment, and then minus the same type of quantity down at point B. So current at B, and then the length. And so really this is length at A and length at B, but a lot of these are going to end up being the same. So the magnetic field at point A, that should be just the magnetic field produced by wire 1 up here. So that will be mu naught times the current at that point over 2 times the distance to wire A. And then we have times IA and times LA. And now for the second term, we have the same type of thing, the current, but now produced at point B. So, oops, that's a 1. So mu naught current from wire 1 over 2 times RB, and then times IB minus LB. So I'm just writing this very generally so it's a little bit more applicable, but now we can kind of start to simplify this. So all these currents are actually the same. They all have a value of 3.5 amps. And additionally, especially in this rectangular wire, IA and IB have to be the same since there's a constant current circulating. So I'm just going to call all the currents just value I. And then I'm going to factor that out from all of this, as well as the mu naughts in the 2. And additionally, these L's are the same too. So both the length of segment A and the length of segment B are both 10 centimeters or 0.1 meters. So we can just say this is mu naught, and then we have 2 I's, so I squared. Those are both just 3.5 amps over 2, and then times just L since they're the same L. And now that's over times 1 over RA, so this distance, 0.03 centimeters, or 0.03 meters, and then minus the distance from here down to the second wire. So that should be 3 centimeters plus 5 centimeters, so 0.08 meters. So those are both meters. And so now we have everything. So our L is 10 centimeters, and our I is 3.5 amps. And so we evaluate that, and we get 5.1 times 10 to the minus 6th newtons. And so given that we've been kind of implicitly calling up the positive direction here and down the negative direction, so that means this will be in the positive direction. So overall, this rectangle of wire is being attracted up towards the long string of wire.